Hello everybody, we are back. In this video, we are going to start Chapter 2, which is all about acids and bases. And this is a subject you've heard a lot about throughout the years. I'm sure you guys went over acids and bases in high school, and of course you went over it in Gen Chem as well. We're going to review a couple of concepts that you've talked about before, but also in this chapter we're going to take a pretty decent chunk of time and dedicate it to something that you probably have not done before, and that's looking at different structural effects to actually determine what is more acidic and what is more basic. All right, a good place to start is just simply by reviewing one of the common definitions. Right, you've learned several different classification systems of acids and bases throughout the year. One of them is called the Bronsted-Lowry definition. And, usually when we're talking about this in class, just for brevity purposes, a lot of times I'll call it Bronsted acids. Other places do too. I feel kind of sorry for Lowry, but hey, he should have known better than to have been second in the alphabetical naming system. So we're just going to call them Bronsted acids, but it's the Bronsted-Lowry definition. Right? And it's very important to keep these definitions straight because it is easy to kind of mix them up. Bronsted acids are known as proton donors. They like to give away protons. And when we say proton, basically we mean H+. All right? And you guys are well aware of several common Bronsted acids. You've learned about hydrochloric acid, HCl, sulfuric acid, H2SO4, nitric acid is another common one, HNO3. Right? The hydronium ion itself, this is what actually forms whenever an acid is dissolved in water and it gives off its proton. The water can accept it and becomes hydronium. Water itself can be an acid. It can actually donate a proton. Ones that you might not think about. Something like this. This is an organic acid. Right? This type of acid right here, this specific one is called acetic acid, and you've probably heard of acetic acid before. It's found in vinegar, right? So you've encountered it in everyday life and lab applications before. Acetic acid is an example of a larger group of organic acids called carboxylic acids. Okay, so there's lots of other types of there's lots of other carboxylic acids as well besides acetic acid, but they all have this structural feature in common, the one I'm circling right there. Okay, and there's oodles and oodles of other examples of Bronsted acids I could go over, but just kind of wanted to jog your memory a little bit and remind you of what they look like. They all have available protons that can be donated to something else. All right. By the same token, we can have Bronsted bases. These are just the opposite. These are going to be proton acceptors. Right? They're going to incorporate an H+ into their structure. All right? And one thing in common about all Bronsted bases is that they have to have something there to actively accept the proton, right? So what does a positive proton, an H+, want to bond with? It wants to bond with something with extra electrons, all right? So anything that's going to be a Bronsted base is going to have some unshared pairs of electrons and or pi bonds, pi electrons, all right? So some examples. Again, you've heard of some of these, good old OH-, right? And just so you can see, I'm going to illustrate the electrons. There's the hydroxide ion, right? You guys have heard of sodium hydroxide, calcium hydroxide, magnesium hydroxide, etc. These are all sources of the hydroxide ion, and it's the hydroxide ion itself that acts as the base, as the proton acceptor. You could have something like this. OR-. Just a little note here. Whenever I say R, I'm referring to a generalized carbon-containing chain, right? R can be R basically just means the rest of the molecule, right? It could be like a CH3 group or CH2CH3 or whatever, right? These guys are called alkoxides, right? And so, like I mentioned, you could have CH3O minus, that would be an example. You could have CH3CH2O minus, etc. Ammonia is a common one. You guys have all heard of ammonia, common cleaning agent. This one's actually not negative like the other ones. It's neutral, but it does have an unshared pair on nitrogen that can incorporate a proton. Water itself. Yeah, we said water can act as an acid. Well, it can act as a base as well, just depending on its surroundings. It's got two unshared pairs. Even something like this kind of looks funny, right? This is acetone. It can accept protons. It's got two unshared pairs of electrons on oxygen, and it's got a pi bond. In fact, we don't even need to have unshared pairs. Something like this, that double bond right over here, that pair of pi electrons is available in certain cases to accept a proton, right? So, yeah, there's lots of different things, but they all have in common the fact that they have available electrons to accept the proton. All right? So there's kind of a review of some examples and definition of Bronsted acids and bases. Let's see them in action. All right? If you want to draw, we use BL for Bronsted-Lowry. Give Lowry a little credit there. Bronsted-Lowry reactions, just generally speaking, you have something that acts as the proton donor, HA, right? That's the acid. And you have something that acts as the base. And it's going to have available electrons. Sometimes it's neutral, sometimes it's negative. That's going to be your base. All right? And what happens is the electrons, actually I'm going to adjust this one a little bit just to show you the mechanism a little bit better. Ooh, I accidentally went into sparkly font there with my H. Hope you enjoyed that. All right, so the electrons from the base can come over and grab that hydrogen, and that allows these electrons to be retained solely on the A. All right, so in this case, we end up with HB, right? And the B was neutral in this case. It gains a proton, so now it gets a positive charge. If it had been negative, it would have gone to a neutral charge. And then we have A minus left over from loss of the proton. Okay? HB is what is left of the base after it accepts a proton. That's called a conjugate acid. I'm going to abbreviate that as CA. The leftover after the acid, the original acid gives up its proton, and it's A minus in this situation, that's going to be your conjugate base. If we want to see real examples of this, right, we could have something like this. We could react water and ammonia, for example. Right? In this case, ammonia acts as the base. I'm just going to write B for base. It's going to grab it's going to grab a proton from the water. These electrons will go to the oxygen. So since water is giving up its proton, it's the acid, and you form OH minus, right? That's the leftover from the acid, so that's the conjugate base. And you form the ammonium ion, and the nitrogen has a positive charge. That's your conjugate acid. Okay? Hopefully this all brings back memories. You guys have done this before. Shouldn't be too difficult. All right. Let me show you another example here. All right. We could have HCl, it's hydrochloric acid, reacting with CH3O OH. Same thing, right? HCl is going to be the acid, so it's going to give up its proton. It's going to give it up to the oxygen in the second molecule by using a pair of electrons. These electrons will go back over to the chlorine and oops, we get Cl minus as our conjugate base and CH3OH with an extra H on it as our conjugate acid. All right? Yeah, very, very simple. Now, one thing that you may be asking yourselves, though, is how do I know initially which one's going to be the acid and which one's going to be the base? Right? Well, there's a couple of different ways you can go about that. Right? For example, in this one, right before I erase it, in this one you see HCl, well, it's got an H. CH3OH, well, it's got several H's. How do I know which one actually gets rid of a that's annoying. All right, apologies for that. All right, anyway, they both have H's. So how do you know which one is actually going to give up the H and which one's going to accept it? Well, like I said, there's a couple of different ways. The way that you guys have learned how to do this in the past is by looking at something called the pKa value. All right? So there's a guideline. The lower the pKa value for a given species, the stronger the acid, right? And the stronger the acid, the more of a tendency it has to give up its proton, right? So if you look at a couple of reactants, you can just look up their pKa's and see which one of them has the lower pKa. The lower pKa material is gonna act as the acid. You know, we did a system with water and ammonia. pKa of water is 14. pKa of ammonia is 37. We did another system that had HCl and methanol, which is CH3OH. Methanol has a pKa of 15.54, and HCl has one that's negative 6.3. And that makes sense. It's a strong acid, so it should be really, really low. In fact, it's so low it goes below 0. All right? So that's one way that you can go about figuring out which one's going to be the acid, which one's going to be the base. All right? And you've done this before. All right? And there's several examples in your book. If you need a little bit of review going over this, be sure to work through those and sort of look through those, you know, to kind of get a hang for this. Like I said, you've done it before. However, what I want to show you now is I want to start showing you anyway, an alternate way of doing this. We're organic chemists. We don't need no stinking pKa charts. We can just look at the structure and figure it out. Yes, we can. Lo and behold, what we can do is we can look at 4 different structural effects. And these are going to be features of the chemical structure that give us insight onto why something might be more or less acidic than another species. All right? I'm going to write these in order of importance. The most important one is called the element effect. This is the strongest out of the 4 effects. Okay? Numbers 2 and 3 are pretty similar, so these can sort of be interchangeable at certain times. Sometimes one is more powerful, sometimes the other one's more powerful. It just depends. All right, the second one I'm going to list is something called the inductive effect. This is a V in case you can't see it. The third one is called the resonance effect. And the fourth one is definitely the weakest of these four effects. It's called the hybridization effect. And you might get an indication from kind of looking at some of these names. We just went over in chapter 1, we went over resonance, we went over hybridization. Electronegativity is going to play a part in a couple of the effects. You can see where the stuff really all sort of starts to tie together. All right, so these are the four effects. And basically there's a process that you can go through to see if any of these effects are active in a given example or not. All right, here's what you want to do. All right, let's say that you're given two species and you're trying to figure out which one of them is going to act as an acid, which one's going to act as a base. All right, here's the steps. Number 1, draw the theoretical conjugate base of each starting compound. All right, just get some scratch paper and draw what their hypothetical conjugate bases would be if they lost protons. All right. Number 2, look at the conjugate bases and determine which conjugate base is more stable. And this is where you use your effects. If you look at two conjugate bases, you can say, well, this one is being more stabilized by the element effect, for example. So this one's a more stable conjugate base. These are the judgments that you have to make. Once you figure that out, you can apply this. The more stable the conjugate base, the stronger the acid that produced it. And that makes sense, right? If you're going to take an acid and you're going to remove a proton from it to make a conjugate base, and that conjugate base is really stable, right? That means that conjugate base should be pretty easy to form, right? And if it's pretty easy to form, that means it's easy to pluck a hydrogen off. The more of a tendency to pluck off a hydrogen or give up a hydrogen, the more acidic you are. All right? So let's take a look. Let's start taking a look at these different effects. And I'm going to start off with the element effect, the most important. All right. Okay, the element effect deals with the atom that directly loses the proton. All right. Let me give you an example here. Let's compare a couple of different molecules. HCl versus dihydrogen sulfide. That's H2S. Okay? All right, so what we can do here, this is one that we can pretty easily draw the conjugate bases for. If HCl were to give up its proton, you'd be left with Cl minus. If H2S gave up one of its protons, you'd be left with SH minus. All right. The charges are on the respective atoms. The negative charge is on a Cl, and the negative charge is on a sulfur. Right. So you have to determine basically which one of these atoms can better handle a negative charge, a Cl or a sulfur. And we can use the element effect to figure that out. All right. Let's look at a periodic trend. If we go from left to right on the periodic table across a row, you see that we increase in electronegativity. Okay? We get more and more electronegative as we go across. Remember, electronegativity is the tendency of an atom to basically to hold electrons. The more electronegative something is, the more it likes to hold electrons, right? And electrons are negative. right? So as you go from left to right on the periodic table, you're getting to atoms that are more and more able to withstand extra electrons and extra negative charge. For that reason, if we're looking at this, we can also say as you go from left to right, atoms have increasing acidity. And that makes sense if you look at these two, right? Cl minus. If you look at Cl minus, if you look at Cl and S, you'll find that they're in the same row on the periodic table, right? Cl is just one to the right of S. It goes S and then Cl, left to right. All right. Cl is definitely more electronegative than sulfur, so it's going to be able to better handle a negative charge. All right. So between these two, Cl minus and SH minus, Cl minus is more stable. That means it comes from the stronger base, and we can say that HCl is stronger than H2S. So if these two were to react, HCl would give up its proton, and H2S would accept that proton to become H3S+. Okay? Let's try another one. Let's try this. Let's throw a little organic structure in here. Let's try this. This is an organic molecule commonly known as an amine. And this is water. All right? Well, first of all, you can actually use the element effect to determine the most acidic protons within a molecule as well, right? If you look at this structure on the left, we actually have 3 different sets of protons. We have, 3 H's here, 2 H's on this carbon, and then we have 2 H's over here, right? So again, if you're confused about which one of those is going to be the most acidic atom in the molecule, you can use the element effect. If we were to lose an H off of one of the first 2 carbons, we would be left with a C minus. If we were to lose an H from the nitrogen, we would be left with N minus. And you have to ask yourself, which one of those is more electronegative? Which one of those is better able to handle a negative charge? And the answer, of course, is nitrogen, right? It's further to the right on the periodic table. So if this were to lose its proton, it would lose one from the nitrogen to give you that. H2O, obviously, would lose from one of the 2 from oxygen, so you would form this, OH minus. Okay? So again, you have to ask yourself, which one of these is the more stable conjugate base, the more stable situation? Is it going to be negative nitrogen, or is it going to be negative oxygen? Well, just look at the periodic table. OH minus is more electronegative. It's going to be able to handle the negative charge better. And out of these 2, water is going to be most acidic. Okay. Hopefully that made sense. By the way, as always, if you have any questions, just be sure to send them to me or bring them to class or whatever, or drop by my office. I'm a lonely hermit up in my office since Andy never comes by, so I need the company. All right. Now, there is another factor to the element effect just than a periodic trend across the row. All right. We can also see patterns going down a column, and this is kind of interesting because some of it is a little counterintuitive. All right. Let's take a look at a periodic trend going down the column. All right. We see as we go. Not going down the column, going up the column. Son of a nutcracker. Okay. There we go. Okay, so another periodic trend that we can see regarding electronegativity is that as we go up into a column, we increase electronegativity. All right? So, like, for instance, if you're looking within the halogens, fluorine, chlorine, all those. You'd see iodine, is at the bottom. It's a lot less electronegative than fluorine is, which is at the top of the column. So, what do you think the pattern would be with acidity, right? You might be surprised. Actually, as you go up, you decrease in acidity. And that's kind of weird, right? Because we saw, with the row, if we increased electronegativity, we increased acidity. But it's actually backwards here, right? That's because there's another factor at play besides just electronegativity, and that's going to be the size of the atom, right? As we go up a column, we increase in electronegativity. However, we also, come on, there we go. We also decrease in the size of the atom, right? The bigger atoms, of course, are at the bottom of a periodic table column. The smaller ones are at the top. That's going to be important. Size is a major factor here in how stable the electrons are going to be in your conjugate base. Right? Here's a good example. Let's compare HI versus HF, right? Hydroiodic acid versus hydrofluoric acid. And again, we could draw the conjugate bases, right? Obviously, you would be left with I minus, and you'd be left with F minus. Just like the grades you're going to get in OChem. Ha 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 ha. Just kidding. I hope. Anywho, if you look at these, you can ask yourself, well, which one's more stable? Well, F-fluorine is certainly more electronegative than iodine. That's not an issue, right? So you would think it would be able to better handle the negative charge. However, let me redraw these conjugate bases in a little bit of a different way to sort of illustrate how size can have an effect. All right, iodine is much bigger than fluorine. All right, so if I were to draw these to more of a scale, I could represent I minus like that, and F minus kind of like that. All right, I is much bigger. All right, so in fact, I didn't have enough room to draw my negative charge. Let me try that again. That's better. All right, so when halogens have negative charges, they have 4 unshared pairs of electrons. All right, so iodine, they can spread out. You can have a couple here, a couple here, a couple here, and a couple here, right? Whereas in fluorine, they're all kind of bunched close together around that one little tiny fluorine atom. Remember what I said when we were talking about resonance. Electrons like to spread out whenever possible. You don't want to have a concentrated electron density, concentrated charge in one particular area. The more it spreads out, the more stable it is. So there's an interesting situation here, right? Within a column, the size sort of outweighs what you see with electronegativity. Fluorine's more electronegative, sure, but iodine just has so much more room for the electrons to spread out. Sorry, I'm fighting the hiccups, so if you hear a funny noise, please excuse me. There's so much more room to spread out with iodine. This is going to be the more stable conjugate base, and as a result, HI is a stronger acid than HF. In fact, HI is classified as a strong acid, and HF is classified as a weak acid. So yeah, that's something else you have to take into account whenever you're comparing acidities. Right, so if we were to compare, I didn't mean to lapse into red ink here, but whatever. If we were to compare HBr versus HCl, you would have the same argument, right? You'd be forming Br minus in one case, you'd be forming Cl minus in another case. Cl is more electronegative, but since Br is a bigger atom, it's actually going to be a little bit more stable as a conjugate base, and HBr is a more powerful acid. H2O versus H2S, right? They're both in the same column. However, sulfur is a little bit bigger than oxygen, right? So you'd have a negative sulfur versus a negative oxygen. Oxygen's more electronegative, but the size difference means that H2S is actually going to be the more acidic molecule. All right? So in summary, there's two features you have to look at with element effect. That's going to be electronegativity of the atom that loses the proton, and also its size. All right? So that's the first effect. We're going to look at 3 more. I am going to continue those in a later video. All right? So until then, I will talk to you later. Bye-bye.